S, but then the first three must be specified to a particular orbital. The other four, which is the spin, has to do, are going to be spinning around, or that's how the electrons occupy that orbital. So we mentioned that one, we can have what you call the principal quantum number, the principal quantum number, which we represent with n. And that is also trying to show us the specific energy, what we call the energy levels. So these are the energy levels. Okay, and that the values of n can be 1, 2, 3, 4 to infinity. That's a principal quantum number. Then we can also talk about the angular momentum. So sorry, angular momentum, and the angular momentum, which is also known as the secondary quantum number, which we represent with L. And that has to do with the subshell level. In other words, the orbitals. So it's either the orbitals or what we are calling the sub-levels. So we have levels, and then in that levels, we can have other sub-levels, which we represent with the orbitals. And that L has an allowed values from 0, 1, 2, 3 to infinity. Now, the value of L depends on the value of n. And so it's going to be like the value of n depends on the value of n, which has to do with n minus 1. Now, what's the representative of the orbitals? Well, the 0 represents the s orbital. 1, we said, represents the p orbital. 2 represents the d orbital, and then 3 represents the f orbital to infinity. So j, h, so we can go from that point. Well, that's the allowed values of so the allowed values of the n, L. Well, we also kind of notice that, so in every energy level, so I made that example, I cited that example using the NLT. So the NLT building becomes the energy level, which is the, the n, the principal quantum number. Then the classroom becomes the orbital. Okay, now when we get to the classroom, we can have what we call the magnetic quantum number. So we can have the magnetic quantum number, which has to do with how the orbitals are going to be orienting themselves when they come to contact with a magnet. So that's specific orientations of these orbitals. Now the allowed values start from the minus L through to 0 through to plus L. On the value of L, ML can be oriented. So for example, if, I hope you can hear me, I'm just doing some form of revision.
Yeah.
Okay. So if, if L equal to 0, then the ML, or the allowed value for the ML, will be just only one orientation, from negative to positive 0. We don't have negative 0, we don't have positive 0. So that the ML will just be 0, meaning it has only one orientation. If L equal to 1, so that is the s orbital. If we have s orbital, just one orientation. Now it will be getting into different energy level, but then the same shape, it will not be orienting, only that as you go higher, then the size increases. but that is not the orientation is just the same. Now, when we take ML to be equal to 1, the ML orientation will start from -1, 0, and then +1, meaning we can have 3 different orientation for that. And 1 is said to be the p orbital. So what it means is that the p orbital can have 3 different orientation. While in terms of direction, we will say that the p orbital orients itself in the XYZ direction as a px, the py, and then the pz. So if I say that orientation in terms of that, if this is x and this is y, okay, or this is x, this is y, and then this is z, we can have the 3 orientations. So for example, in the x orientation, we can have that. In the y orientation, we can have that. And then in the z orientation, we can also have that. 3 different orientation. Now, if L equal to 2, sorry, if L equal to 2, then ML will be having 5 different orientation, which is -2, -1, 0, 1, and then 2. If you count it, this is 1, 2, 3, 4, 5. And this is the D. 2 is the D orbital. So the D orbital has 5 different orientation. And in terms of X, Y, Z direction, then we can say that this is DXY, DXZ, D, so YZ, then the DX squared, Y squared, and then the DZ squared. 5 different orientations for the D orbital. Now, if L equal to 3, which is the F orbital, can you tell me how many orientation that will be? So the ML will have how many orientation? Oh, I hope you can hear me. So let me see. If you can't talk, you can equally do the chatting, can chat, and then I can know you are there. Okay, so if yes, so if L equal to 3, what will be the allowed values for ML? That will be 7 different orientation for L equal to 3. So we're going to have -3, -2, -1, 0, 1, and then 2. If you count it, that's 7. 1, 2, 3, 4, 5, 6, 7. So we don't know how the F orbital, that's a fundamental orbital, behave in terms of the XYZ. So we'll just say that we have F1, F2, F3, F4, F5, F6, and then the F7. These are the fundamental orbitals. Now we can just have some, we can derive some things from what we are just looking at. And one thing is that once I know the N, if I know the N, I can know the number of orbitals that the N can occupy. That is, if I know the energy level, I can tell how many orbitals must be in that energy level. Well, how do I know? If I know N and I want to know the total number of orbitals that should be there. If I want to know the total number of orbitals, then basically once I know N and then I square N, it can tell me the total number of orbitals that are available in that energy level. For example, if N equal to 1, then the total orbitals which we should be getting is 1 square, which is same as 1. You get me? So basically,
yes,
if I know that, so basically, if I'm looking at the allowed value, if n equal to 1, the allowed value for L will just be 0. That is n minus 1. So that is 0. That's the allowed value. So it means that the allowed value will be just 1s. That's the only value that I can be getting for energy level 1. If I go higher to, say, energy level 2, what do you think will be the total orbitals there? So that will be 2 square, and 2 square is 4. Now, what's the total energy? So if I get to the energy level 2, the total energy will be 2. Well, if I'm using the, so if n equal to that, so that will be 0 and then 1. That's the highest you go. So that is S and then P. So for 2, we can have S and P. P can have different orientation. So we can have Px, Py, and Pz. And so we have 1, 2, 3, 4 orbitals in that energy level 2. Am I making sense?
yes, sir.
Okay. Now, so that is n, if I know n. Now note that when n, so for example, when n equal to 3, they allowed, again, I use my words very careful, they allowed values. Please, please. I don't know why sometimes we have to talk before we do the right thing. You can have sense to unmute yourself, but you can't have sense to mute yourself. I don't know what's going on. So if I have n equal to 2 and 3, then the allowed values is 0, 1, and then 2. The maximum that we can get for L is going to be n minus that. So that's the highest we can get to. So this is S, P, and then D. So if I come to the third energy level, I should be getting 3S, 3P, and then 3D. That's the highest. And this one is in 3 orientation. This one is in 5 orientation. So if you look at it, the total number of orbitals there should give me 9. So n squared is equal to where n is equal to 3. Therefore, 3 squared is 9. So the total number of orbitals in that energy level is supposed to be 9. And sometimes, because we don't want to be including the directions, but we know, so we just write P. So for example, 2P, but then we should note that the 2P is in 3 orientation. Later we understand that each orbital can only take 2 electrons. So if you just write 2P, then it means that if you are not considering the direction, then 2P can only take 2 electrons. But then P has also different directions. So each of them is taking 2, 2. So P can now take 6 electrons. So that is N. Now, what we want to also derive from L is that once I know my L, which is also trying to say that we have the orbitals, then basically the L should also, we should know that one, of course, if you are looking at it, 0 is lower than 1, 1 is lower than 2. In other words, S orbital should be lower in energy than P, and P orbital should be lower in energy than D, and D orbital should be lower than in energy than F. So 0 is less than 1, 1 is less than 2, 2 is less than 3. Are you okay? So when we get to a point, we will say that when we are filling the orbitals, we should fill the lower energy first. So note that in the orbitals, we have different levels, although they are all in the same kind of orbital, energy level. So like the NLT and then the classroom. So although they are all aptech students in the class, definitely we have some that are program rep, we have course reps, we have so and so. So at least some differences comes in. Is that okay? Now, note that, as I mentioned, when we have N, now N is related to L by just noticing that the highest or the allowed value for L should be N. That's the highest. And so if we have a situation where L is more than that, we'll say that that is electronically, it is forbidden. For example, if N equal to 2, and then they write that L equal to 2, this is forbidden. In quantum chemistry, this is not allowed. In other words, you want to say that we should have 2D. It's forbidden. There's no way the electron can jump to that higher kind of, can change to that higher orbital. So we say that it is electronically forbidden. Are we making sense? Okay.
Yes.
Now we will come to the ML. We said that the ML is going to be having an allowed values from a negative L through to 0 to a positive L. And that has to do with the orientations, okay? And that's it's the orientations of the orbitals. And of course, the orientations of the orbitals are also as a result of the energy level, which will give rise to the shape of the orbital. And of course, so in each energy level, we can have different shapes of orbital. That's the S orbital, P orbital, D orbital, and the rest. Now, for this, when we get to the ML, we can notice the number of electrons each orbital can be accommodating. Now, how do we know that this will be the number of orbitals that each orbital should be accommodating? So these numbers will try to see how the individual orbitals can hold how many electrons. Now, we've mentioned earlier that each orbital can take 2 electrons. So if I have say 4 total, so I'm coming back to this. So if I have a total of 4 different orbitals, what do you think should be the number of orbital electrons that can be accommodated in that energy level?
8.
So that would be a total of 8. Do you follow? Okay.
Yes.
Yeah. Now the last quantum number which we mentioned earlier has to do with the MS. I don't know if I'm missing something. So okay. The last quantum number we mentioned was the MS. Now we said that the MS can either be plus half or a minus half. That means that it's going to be pointing up or it's going to be pointing down. That's how, or the interpretation of what MS is. How many times will I say this? Who is that Precious Adekun? Okay. So let's try to play around before I make progress with this one. Now, can you tell me what will be the angular momentum, that is L, and then the magnetic quantum number when I know the principal quantum number to be n equal to 3? Can you tell me the allowed values of L and then the allowed values of the ML? Just as I mentioned, you can be typing it, or you can, if you want to say that, you can also say that. What do you think will be the allowed values of the n equal to 3? Okay. So for n equal to 3, L, the allowed value should be 0, 1, and then 2. That's the allowed values. Now, if I take L equal to 0, the ML is just going to be 0. That's just one orientation. If I take the L equal to 1, the ML should be 1 through -1 to minus positive 1. Now, if I take the 2, L equal to 2, the allowed value should be -1, -2, 1, 0, 1, and 2. So different orientation. So if I'm looking at it, if I take n equal to 3, the allowed kind of the total number of orbitals which will be available is going to be 1, 2, 3, 4, 5, 6, 7, 8. So 5, 6, 7, 8, 9. So I've mentioned that earlier. So 9 different orbitals in that energy level. But then the ML is that, then the L, it's also that. Does it make sense?
Yes.
Okay. Now, for example, if I should, so that we can flip it. So if, for example, I should write 2D, and I ask you to give me the value of N, the value of L, and then the value of ML. What will be the value of L? N. Yes, what will be the value of N? Well, the entire question is forbidden. It's forbidden to tell me that 2D exists. So I should tell you the principal quantum number, then the L or the D. That's forbidden. However, if I should write 2P, then N equal to 2, L can be what? What's L? What's the value of L?
L is 0, 1, and 2.
It's what?
0.
No, it can never be. It can never be 0 and 1. Please look at it very well and tell me. 0, it means S orbital. There's no S orbital there. Why are you saying it is? When we say the allowed values, does not mean. So we have specifics. Do you understand?
Yes.
So here, for example, in this case, it was hoping that when I get to energy level 3, I can have S orbital, P orbital, D orbital. Okay, so if I should just choose just one of them, like 3D, I can't say that L should be 0, 1, 2. No, that the L there is just 2, the N here is just 3. And if I have electrons on that, then I can just look at that. Now from here, the ML can either be any of the orientation. It can be -1 or it can be 0, or it can be 1. That means that it can be X, PX, or it can be PY, or it can be PZ. So that will be the ML. Is that okay? Okay. Now let's see if you are following that. Now, can you write it this in terms of the orbital representation for me? So let me close this. So we want to write this. So if n, to identify the orbital, if n equal to 3 and L equal to 1, and then ML equal to 1, can you write the representation of these quantum numbers? Yes, what's the representation? Yes. Who is talking? So the representation will be the energy level is 3, L equal to 1 is P, and so we can either write PX, PY, or what? That is just that. So that is either P, 3PX, 3PY, or 3PC. That representation can be correct. Are we okay? Okay. Again.
So you didn't add the one.
Which one?
Like 3px1.
Where is the one?
The ML, right? It's 1. So like
ML has
3px1.
What is ML? What did I say ML is?
The magnetic
So
quantum.
ML, yeah, so that's just showing the orientation. If you wanted to add up electrons, that is where MS comes in.
Oh, okay.
Are you okay?
Okay, sir. Yes, sir.
So electrons are the positions of the electrons are the spins. So if it is 1, we'll just write half. If it is 2, can either write plus or minus half or just 1. That shows you the electrons, the number of electrons. But let's take it slowly. Now, what will happen if n equal to 2 and L equal to 0? How do we represent this?
So
Yes. So that's basically is going to be 2s. Are we okay? So that will be 2s. Okay. So basically, once we know the we can tell the energy level. That energy level can give us an idea how many allowed orbitals should be available in that energy level. We can even calculate the total number in each energy level. Then from that orbitals, we can also notice the orientation, which is the magnetic quantum number. And then we can now include the electrons. So whether the electrons are pointing up or they are pointing down. So that's where we have the magnetic spin coming in. So for example, if I write, say 2p1, so there let's say 2px1. If I want to represent this in quantum numbers, n is equal to 2, L is equal to what? What is L?
L is equal to 1. Hey.
1. ML is either -1 or 0
or one.
So that's numbers. We don't kind of restrict it to any. So we can say ML is 1. Then the MS is going to be minus half or plus half. What does that mean? What it means is that the one electron can be pointing up, or that one electron can be pointing down. That's what we mean by the electron spin. Are we okay? So the number of electrons, which we know that the highest an orbital can take, is just 2 electrons. So it's either going to be all of them pointing up, which is 1, or all of them pointing down, if 2 electrons, or one is pointing up, one is pointing down. So if we have more than 2 electrons in the magnetic spin, what will be is that then we'll sum up all the electrons there. So we sum up all the electrons available, then we indicate that. Okay, so having this idea, then let's make progress from that point. So having understand these quantum numbers, then the Pauli or this Wolfgang Pauli, please, I'm saying that again, please. Don't know why it's taking me time to remove this person. So I will not be given any kind of chance again. I can't verify who that is. Okay. Yeah, so let's make progress. So it means that in each energy level, we can understand the number of allowed quantum numbers that are going to be represented there, and then the number of electrons which can also be represented in each quantum number. Now, Wolfgang Pauli kind of gives us an idea how to deal with this. Now, that's what we call the Pauli exclusive principle. And the Pauli exclusive principle states that no 2 electrons can be in the same kind of atom or quantum number. So what it means is that when we are trying to fill the orbitals, we can allow them, all of them, to be occupying the orbital taking more than 2 electrons. So this means that again, no 2 electrons can occupy the same orbital. So in other words, if I have the s orbital, so if I have the s orbital, I have the px, py, pz, and then those kind of orientation. No orbital can take more than 2 electrons. That's what Pauli exclusive is trying to point to us. Does it make sense? If these 2 electrons are going to be in the same orbital, then they have to be pointing in opposite direction. We don't get to, so that when we bring it closer to the magnet, once they will be pointing up or they are going to be pointing down. So they can't take more than 2, but the 2 that they take, the maximum 2 that they take, they should not be pointing the same direction. The spin should be in the opposite direction. Now again, if an orbital is going to be having just 1 electron, it makes that orbital become para. So that is when we bring it closer to a magnet, that becomes a paramagnetic. Okay. Now, if the orbital is going to be in opposite direction, that makes it die. And so when we bring a magnet close to it, that becomes a diamagnetic. It gives it a diamagnetic property. Now let me explain that. The paramagnetic property means that, well, of course, you can see just one electron, and then the magnet also has electrons around that. So basically what is going to be happening is that it will draw the magnet to itself. It will draw such an electron so that that orbital can be full. So paramagnetic properties of these substances will be that property that allow that substance to draw electrons to themselves. And then the diamagnetic will be repairing the electrons. So that will be, they'll be repairing the magnets away. So that's the what you can derive from Aufbau. Now, in terms of distributing the electron, then we have to look at the building blocks of how we distribute the electron. And that's so the first kind of principle that I stated has to do with the, so that's the Pauli. So from Wolfgang Pauli, it's called a Pauli exclusive principle. Another principle which I want to mention is the Aufbau. So that's the Aufbau principle. So the Aufbau principle. And what is this Aufbau principle? What is this Aufbau principle? Well, so what's this Aufbau principle? So the Aufbau principle basically means we should start from the building blocks. That's try to build it from lower to up. So build it up. So start from a lower energy before getting to a higher kind of energy. Now, if you look at it, so let's see if we can build that. Now, if I have energy level 1, the allowed kind of orbital there will be 0, which is S. If I go to energy level 2, that I'm going to be having 0 and then 1. That is 2S and then the 2P. If I get to energy level 3, so I'm going down the energy. If I get to energy level 3, the allowed values will be 0, and then 3, 1, and then 3, 2. That is 3S, 3P, and then 3D. Energy level 4 will be 4S, 4P, 4D, and then 4F. Are you following? So that will be for energy level 4. If n equal to 4, the allowed values for L should be 0, 1, 2, and then the highest will be 3. That is F. This is F, this is D, this is P, and then this is S. So their highest will be the n-1, that is F. If I get to energy level 5, can you tell me the allowed orbitals there? Energy level 5 should be 5S, 5P, 5D, yes, 5F. Well, theoretically, we can have 5G and whatever. Now, if I get to energy level 6, that will be 6X, 6P, 6D, 6F, and again, theoretically, we can be going on. If I come to the last energy level from all the periodic table, we can only have N, the maximum is N equal to 7. But theoretically, we can go to infinity. So 7, well, if you are starting from 7, well, we can get to 8 as well. So if we take hydrogen out, so 7 different periods. So 7s, 7p, 7d, 7f. Again, we can continue with that. And that's if we take hydrogen out, that will be the 8. Theoretically, we can get to 8, but then in reality, we'll just have to be ending with the 7 energy level 7. Now, Avban says that if we want to be filling
Hello,
the
sir.
orbitals, yes,
Hello, sir. Sir,
yes,
please, the letter attaching to the number. About as far as the number is increasing, is the letter going to be in arranged form or what? Hello.
I didn't get to the last part of what you said.
We share 7 now. On the 7, you'll be getting 0 up to 6. But
Yes.
PDFG, you know, the material origin from alphabetical in an answer there.
Alphabetical says they are arranging based on the say if you take energy level 7, if you take energy level 7, the allowed orbitals will be 0, 1, 2, 3, 4, 5, and then the highest will be 6. So now
Yes, sir.
And now where S, where P, where D, where F. The account will be a theory. Until J, H, I, J, K, L, M, N, O, Y. A theory. It doesn't exist.
Okay, thank you, sir.
Yeah, so theoretically we can start with I mean, that's why the F becomes the fundamental. So we have G, H, I, J, but it doesn't exist.
Okay.
Okay. Now, Afban says that when we are going to be filling these orbitals, knowing well that Pauli says that no orbital can take more than 2 electrons, and even that the 2 electrons should not be facing the same way. It should be oppositely, I mean, facing the opposite direction. Now, the Afban principle says that these orbitals, some of them are higher in energy than the other. Even within the same orbitals, some are even higher than the others. Okay, so the orbitals are assumed to be on the same energy level, which we call degenerate orbitals. Now, even in that, some are slightly higher in energy than the other, especially when we get to the d orbitals. So in the d orbitals, you can have 3 of them be on the same energy level. Then the dx, dy will be a slightly higher in energy than the rest, and the dz squared will also be higher than the dx squared, y squared. But they are in the same orbital. So it's like you've gotten to the classroom. Now, when you got to the classroom, just as I mentioned, there are some that are course rep. There are some that are program rep. So we want to say that, okay, the course rep is restricted to course, but the course rep is higher than the other class student. But then the program rep is also higher than the course rep. But then they are all in the same class. Do you get me? So we should just know that. Now, Afban says that when we are filling, let's start from the lower energy. So 1, 2, 3, 4 means that we are going down. As we are going down, the energy is going to be increasing. 1 is smaller than 2. So means that 2 is bigger than 1. So down there, we are increasing the energy. So as we are going 1, 2, 3, the energy is
Yes.
Lisa, you've muted yourself.
So thank you. So we're saying that Avban says that we should be feeling considering the energy level. So 1 is lower than 2, 2 is lower than 3. So as you are going 1, 2, 3, 4, then we are increasing the energy level. Do you get me? Now in filling, Avban says that when you are filling, you also consider the orbitals and how they are quite higher than each other. So when we are filling, we'll fill 1s first. We'll follow it with the 2s. Then the 2, so look at the arrow. So the 2s will come to 2p, then will come to 3s. Then from 3s, we'll come to 3p, and then we'll come to 4s. Now after 4s, we'll come to 3d, then 4p, 5s. After 5s, we'll come to 4p, 5p, and then 6s. Is it making sense? After the 6s, come to 4f, then 6p, then 7s. After 7x, come to 5f, 6d, 7p, and then 8 kind of s. So if you want to continue theoretically, after 8s, come to 6f to 8p, then you'll be going if we have 9 and those stuff. So in other words, if I should write it now, if I'm going to be filling the orbital, so I'll fill 1s, follow it with 2s, follow it with 2p. Then if you look at it, I'll come to 3s. So I have to 3s, it will be the next energy level. After 3s, I'll come to 3p. Now, instead of going to 3d, the 4s is lower in energy than the 3d. So after my 3p, I'll come to 4s, then I'll come to 3d. Then after 3d, if you look at it, after 3d, I'm now going to go to 4p and then 5s. Okay, so that's how the arrow is. Now, after 5s, I need to go to 4p. So after 5s, I'm going back to 4d rather. So I'll go to 4d, then 5p, and then 6s. After 6x, if you look at the arrow, after 6x, we'll go to 4f, then we'll come to 5d, 6p, and then 7s. If you want to continue, then after 7s, you are now coming to 5f, then we'll go to 6d, 7p, and then 8s. This is how Avban sees the arrangement of the orbital. This, oh, sorry, let me lower it. Did you follow that?
Yes, sir.
Yes, sir.
Okay. So when we are going to be filling the orbitals, Avban says that let's start from the building blocks. So the distribution of electrons among the orbital of any element. So that's what we are gradually getting there. It's called electronic configuration. When we distribute electrons among the orbitals of any element, it is called electronic configuration. Now, in each electronic configuration, when we are distributing those electrons, Avban says that let's distribute it considering which one is lower than which one, or which one is higher than which one. So when we are filling, we'll start with the lower energy. So, I mean, if you forget anything, 1 is lower, 2, 3, you are going to infinity higher. So let's fill 1s, then come to start, continue with 2s. Then after 2s, come to 2p, and then 3s. After 3s, come to 3p, and then 4s instead of 3d. But you see, these are energy level 1. This is energy level 2, energy level 3, energy level 4, energy level 5, energy level 6, energy level 7, energy level 8. But so in energy, please, if you can have sense to mute or mute yourself, have sense to mute it back.
Sir, please, you have muted yourself. Sir, please, you have muted yourself.
So you see what happens. So they unmute, then it automatically will mute my own. And when I say that, you can, if you can have sense in unmuting yourself, have sense to mute yourself. Okay. So what I was saying was that if we have energy levels, say energy level 3, now energy level 3 will have an allowed quantum the angular momentum to be 0, 1, 2. That is s orbital, p orbital, and then the d orbital. But our Hofmann principle says that, yes, we know that this orbital exists in that energy level. But when you are filling, the d orbital is higher in energy than the s orbital. So fill the 4s before filling the 3d. So that's the arrangement which we have written here. So if you are filling, we'll write 1s, 2s, 2p, 3s, 3p. And so instead of 3d, we'll fill. Please note that we are not saying we can write, we should write the 4s before. We can write the 3d before the 4s just to notify that this is the energy level. But when we are filling, so this arrangement, according to Pauli, the Hofmann principle, is about when we are filling the orbitals. So when we are filling the orbitals, we'll fill the 4s before filling the 3d. And after the 3d, we'll come to 4p. Now you see, like after 4p, we should go to 4d, but then we'll come to 5s. Then after 5s, we are now going to 4d, then 5p, 6s, and those kind of stuff. So if you forget, maybe you can use these arrows to indicate which orbitals should be filled in your next kind of filling. I hope that will be okay. Can I proceed?
Yes, sir.
Yes,
Yes, sir.
please.
Okay. So this is how we then consider the periodic table and then the elements on the periodic table and see how we can distribute these electrons in the periodic table, on the periodic table. So again, if I draw a skeleton of this periodic table, we're going to be having this skeleton. Okay. Then, so like that. And then we have those that are going to be deviating from that. So we can have this 2. And then we have, say, hydrogen here. We can have helium also here. Now this block this block we call the S block. So we are going to be seeing that very soon. So all the element that falls under this block is the S block. All the element that is going to be falling under this block will be the P block or the P orbital. So let's use block so that we'll group them. Then this will be the D block. And then this is going to be the F block. So when we have a periodic table, the element on that is arranged in this form, meaning when we write the electronic configuration, they are going to be ending with this. So you see that at the S block, you are going to be ending with the number or the energy level which ends with S. Here, we are going to be ending with the energy level, and of course, the energy level will be n-1, but then you end with D. And here, it's going to be the energy level, but then you'll be ending with P. And here, in the F block, we are going to be having energy level -2, then you end with F. So the S block, we are going to be ending with that. If we split it, we're going to be seeing that the S orbital can take 2 electrons. So it means that here we can split it into 2, which is S1, S2. The P orbital can take 6 electrons because we have PX, PY, PZ. So 6 of them. So here in the P block, we can split it into 6. The D orbital can orient it 5 times. Each of them takes 10 electrons. So 1, 2, 3, up to 10 electrons. The alpha orbital, which oriented 7 times, 2 each. So we can split this one into 14 times. Are we okay? Okay. Now I draw it again so that so this is how, now we say that the N has to do with the energy level. Now, that's another way of saying the energy level, which we call shell or period. So in the periodic table, the energy levels are considered as the number, the shares or what we call period. Now we have 7 periods, meaning we can have 7 energy levels. So this is energy level 1. We can have energy level 2. We can have energy level 3, energy level 4, energy level 5, energy level 6, and then energy level 7. Okay. The same way, so if I should put it like this, the same way the p orbitals are also going to bring the same 7 energy levels, including helium. So that's helium. So the same way it's going to be having 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, please. So 1, 2, 3, 4, 5, 6, 7. So this is the 7th one. Okay, let me clean that. Okay, so cleaning that so that it looks nice. So if we take the p orbital and then we take the s orbital, it has that 7. That now for the d orbital starts from the energy level 3. That's why we say it's n. So sorry, n-1. So the d orbital will be n-1. So it will start from here. So a minute. It's going to make 3 points. Okay. So that will be from 3 to just 1 or 2, 3, 4, 5, 6, and then 7. So that's the d orbital. Then the f orbital, that is the Latinite, is going to be having just 2 separation. So that's 2 separation, which is the Latinite, then the Arteninite. Now, if you are writing the electronic configuration, this will be having 1s. This energy level will be having 2s. This is going to be 3s. This will be 4s. This is 4p, 5s. This is going to be 6s. And then the last stage, 7s. Okay. Now, because this is helium, helium belongs to the P block, but then it's going to be having the S kind of. So this is going to be 1s, but then we group helium as part of the P block just because it belongs to the noble element. That's why we put helium there. So helium is number 2, but then when you write the electronic configuration, it will be having S. So it means that for the rest, they'll be ending with 2p, 3p, 4p, 5p, 6p, and then 7p if you are writing the electronic configuration. So all the elements at the P block will be having this ending at the P. Now when we come to the transition element, they will be having, so that is the n-1. So if this is n, their n is number 4. They will be ending at 3d. So that's n-1 times the d. So you have them having 3d. The first rows will be ending 3d. The second rows will be ending 4d. The third rows will be having 5d and then 6d. Sorry, 6d, not f. So that's how, when we write the electronic configuration, they'll be ending with. Now the Latinite will be having n-2 and then f. So if you look at it, they are here. The Latinite are found in period 7 and then period 6 and 7. That's where we can find the Latinite. Period 6 and period 7. So if we have period 6, then it means that they will be ending with 4f and then 5f. So this is how we'll get to have the arrangement of these electrons in the orbitals. So if we are going to be writing electronic configuration, it depends on the where the element belongs to. That's where the electrons will be ending with. So we begin distributing the number of electrons for the orbitals, and then we are using the Pauli, the Afban principles. But the Pauli principles just tells us that we can't get more than 2 in each orbital. But the last kind of rule that we can be showing here is the Hund's rule, which clearly explains the Pauli exclusive, saying that we should be having them paired. So if you are spreading them, then spread them the up and down. So having known this kind of principles and then understanding the quantum numbers, we can now start initiating ourselves to how we can write the electronic configuration using the quantum mechanics, not the classical mechanics. So for example, if I have sodium, let me increase this. Sodium is going to be having atomic number 11. So sodium will have atomic number 11. Now in the classical way, it says that when we are distributing this, we should distribute it such that it's going to be 2, 8, and 1. However, that is quite true, but then the quantum mechanics gives us an idea why this is true. So if we are going to be writing the electronic configuration, for example, sodium, then we'll start from the lower energy which is 1s. S takes 2 electrons. Then we'll go to 2p at 2s. S take 2 electrons. Then we go to 2p. P in 3 different orientation, each of them taking 2. So that P will be 6. Are you okay? Then 3s, but S will take 1. Now this is the explanation. On the second energy level, we have 8 electrons there. 6 plus 2 is 8. On the first energy level, we have 2 electrons. Then on the third energy level, we have just 1 electron. So this is how we write electronic configuration. So it has to do with the number of electrons. And then so we can write electronic configuration for ions as well. So for example, if I have sodium plus basically means I've lost 1 electron. So the number of electrons now is just equal to 10. So I will now write S1s1 2 2s2 and then 2p6. This is 10 electrons distributed.
Sir,
Yes, sir.
sir, please, when writing the 2p, can you choose to expand it and share the electrons on each p?
You say when you are writing
And
what?
The 2p.
Uh-huh.
Can you choose to expand it and be like 2px, 2py, and 2pz?
Yes,
And then
but
share
then
the
to
electrons on it.
yeah, that will be the correct way, but of course, again, not to waste space.
All right, sure. Thank you.
Okay, so not to waste space, I was going to the next step where we write the electronic configuration by using what we call the condensed electronic configuration. In that case, we know the electronic configuration for all the noble elements. So we'll consider the noble element that comes before that element. Okay, then we'll just indicate by just using square brackets, then the rest, because as you are going higher, the electron, if the number of electrons are many, the electronic configuration will be quite long. Is that okay? So what we'll do is that we'll look at the noble element that comes just immediately after that element. Then we'll just put that. So the number of elements that noble element is having, and that clearly will know that that will be ending with a P6. So depending on the energy level, it's going to be on a P6, so that we can now just write the rest for that. So let me give you an example. So say for example, I'm using sodium. Now, which noble element comes before sodium? Can somebody help me?
Neon.
If
Neon.
you have what?
Neon.
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 And what is the electron for the neon? How many electrons does neon has?
10.
10. So for example, neon is number 10. If you have to write the electronic configuration for neon, it would have been 1s2, 2s2, and then 2p6.
Yes.
So if I'm going to be writing the electronic configuration for sodium, which is number 11, I just put neon there. And then I know that after this, I'm going to go to 3s, and then 1. So this is a condensed way. So that I will just cut all these long kind of this thing away. And then I'll just condense that. So, but of course, you should know where the noble element that counts with the elements that you are considering ends. HP electronic configuration. You should know where it ends so that you can continue from there. Does it make sense?
Yes, sir.
Okay. So at least from here, we should be able to write electronic configuration for different elements. And again, we should be able to write for almost all the elements on the periodic table. Would that be difficult?
No.
No, sir.
Okay, so let's try one or two and then see how it will be. Is somebody asking a question? Okay, so you should know your kind of the element and of course the atomic number for that element, and the atomic number for that element will tell you the number of electrons that element is having. For example, let's try the electronic configuration for the following elements. Copper. Copper is number 29. Tin. What's tin is number 50. So let's try the electronic configuration for the following elements. Chromium 24. Potassium. What's the atomic number for potassium? Potassium is number what?
19.
19. Okay. So let's do this. So let's try the electronic configuration for the following.
Hola.
Are you done?
Sir, we are
Okay, I'm waiting.
S, 2S, 2P, 3S, 3D.
Okay, let's see for the copper. So if you want, you can write the long electronic configuration, but then if you want, you can also use the condensed way, the noble element approach. So which element or noble element that comes before copper? I think it's argon.
Argon.
Yes, and I know argon should be ending with a what is it? 3P. Is that correct?
Yes.
So
Yes, sir.
argon, so that's the periodic table I drew for you. So once you know the position, so argon will be ending with 3p6. So what continues? And if you look at it, so if I write argon, how many electrons have I used for argon? 18. 18. So how many left? If I take 18 from this, I'm left with 11, right?
Yes.
Okay, so total of 11 to be distributed. So then we'll now go to 4s 3d. Okay, so don't forget half-band principle. We'll fill the 4s before filling the 3d. But in this case, when we are filling, we'll be tempted to fill 4s and then 3d9. Now, I want to draw attention to something. Well, this is, if you are following procedure, this is how it should look like. However, the d orbital prefer to be fully filled or partially filled to be much stable. The d orbital will be okay when it is fully filled or when it is half filled. So in this case, when we are filling this, we take one from this, it becomes 4s1, then the 3d10. So that's how the copper will be like. In fact, this is what you call the abnormalities of the periodic table. It's quite abnormal. So for example, if I take chromium, for example, chromium, which is number 24, it follows argon, and argon is number 18. So if I take that, how many is left? 18, 24 minus 18, I'm left with 6, right?
Yes, sir.
So this is 4s1, 3d5, not 4s2, 3d4. So this is also deviating from that. So if you take the periodic table, the chromium group and the copper group will be deviating when you are writing the electronic configuration. You have to partially fill the d orbital before or fully filled before you fill the s. Otherwise, the rest follows that. Now, how about tin? Tin is number 50. Tin is number 50, which noble element follows that. I think krypton can be that. And krypton is number 30.
36.
36. So krypton is number 36. So if I take that out, how many is left?
24.
We'll be left with, please come
Yeah,
again.
14.
14. So when we are distributing that, so krypton will be ending at, so if you look at it, 1, 2, 3, 4, so it will be ending at 4p.
4p.
So after 4p, we'll go to 4d, then we'll go to 5s, and then 5p. But then when we are filling, we'll try to fill the 5s before the 4d, before the 5p. Avant principle. When we are writing, we can write it based on the energy level, but when we are filling, we have to fill the lower energy before filling the higher energy. So that D will be 10, 4s, and so 10 will be in the P block. Now, when we write the electronic configuration, we can be getting some kind of information from there based on the valency. So we can see the valence here. So number 5 here tells me the energy level. P here tells me it belongs to the P block, which is number 1. Then the 2 here will tell you, the MS will tell you where, so that's minus half, plus half, so let's use 1. So the information is that when I want 10, I should consider looking at the 5th period in the P block. And then in the P block, the number or the group 2 in the P block, that is where 10 can be located. You get me? So for example, if I want sodium, if I want to locate sodium, which is number 11, it says that in the sodium, I should be looking at the period number 3 or the energy level 3 in the S block, and then the group 1. That's where sodium can be found. So can you tell me how you can? So when you write potassium, the electronic configuration for potassium is 19. So how do you write it? So potassium 19, Can we say that it follows argon? And argon is
Yes.
number 18. And argon ends with the 3p. So the next will be 4s and then 1. Okay. Well, if you are going to be confused with this noble representation, we shorten it. We can still be writing it very long. 1s2, 2p, that's very long. So you know that this one is 10, remaining 19. 3s2, 3p, 6, that is 18. Then 4s, we don't go to 3d, 4s1. So here it tells you that if you are looking for potassium, go to energy level 4. Now in that energy level 4, move to the S block, and then the first group is where you can find potassium. So it tells you the group that the element belongs to, and then in that group, you know the number of elements that are there. So ideally, we can write electronic configuration for any element that we see there. Can we try last one, then I can move on? That's okay. So I'll pick a random this and then we write. Let's write the electronic configuration for iron. Iron, what's the atomic number for iron? That's 26, right? So let's try the electronic configuration for the following. Iron 2 plus, and then iron 0. Hello, can you hear me?
Yes, sir. Yes, sir. Can hear you.
Okay, so let's do the 2, and then we can make progress from there.
Okay, so iron 2 plus is argon for 4s1 3d5.
So it's going to be how many? 3D what? How many electrons for 3D?
3d5.
3D what? 5 or 6?
5.
Please, it's not 5.
8, 6, 6.
Sir, 3D6.
Yes. 3D6, 4s2. You have already fully filled it. It's okay. So then the 4s will take its own 2 electrons. So when you get to 3D9, then it prefers to be 3D10. So you take 1 from the 4s. And again, I said that's the abnormalities of the periodic table, which is the chromium group and then the copper group. Aside that, there is no abnormality there. Those that deviate will then come to the F block. Okay, how about this one? Lead. Lead. What's the atomic number for lead? Periodic table. Lead. Can somebody show me? Lead is 82. So let's try the electronic configuration.
82.
Yeah, so let's try the electronic configuration for lead. Let's see.
Please, sir, we can't hear you.
I'm not saying anything. I'm also trying to write my electronic configuration.
Okay, sorry.
So you two write your electronic configuration. Let's compare. Xenon is number 56.
54.
54. Okay, so 54. So Xenon is 54. 54 minus 80. Yeah, so I'm correct. I don't know about you. So lead will be in the period 6, the P block, and then group number 2. Yes, that's correct. Otherwise, you have to be writing that long, 1s2, 1 long. But then once you know the electronic configuration for that noble element that comes before that, you can just write the electronic configuration. Please, have you finished yours? So this is mine.
No.
Yes. So let's make progress. So 82 minus 54, what will be left will be 28. Is that correct? Now Xenon
Yes,
will
sir.
be on the P, which P? So if you count,
Yeah,
Xenon
5
should be around here. Is that
5P.
okay? 5P. Yeah, so 5P 6. So
Yes,
after
sir.
5P, where are we going? It's 4F,
4F,
4F, and then 5D,
5D, then
6S,
6P.
6P.
Yeah.
Okay, so F takes 14, D takes 10, that is 24. S is 26, then the P will be 28. Okay, so as I mentioned, we should be able to write that for the neutral element and then the charge element as well. So for example, let's write the electronic configuration for nitride, for N3 minus, where nitrogen is 7, right? Okay, so how do we write the electronic configuration for N3 minus? Are you there?
1s2, 2s2.
So what's the total number of electrons we are distributing?
Yeah, 4.
The total number of electrons we are distributing can never be 4, please. We have
It
added,
is 10.
Sir.
yes, 10. We have added 3 to the 7.
Yeah, yes, sir. 10. Sorry.
Okay. So that is
10.
1s2, 2s2, then 2p6. That is the 10 electrons distributed. Okay.
Yes.
How about O2? O minus 2. O minus 2. It's
10.
also 10. So
1S.
it will have the same
1S
electronic
to
configuration.
2S to 2P6.
It will have the same electronic configuration. Is that correct?
Yes, sir.
Like
Yes,
this
sir.
one.
How about C minus 4? C minus 4.
Also 10.
It's
will
also
have
going to have the same electronic
10.
configuration.
Yes,
Okay.
sir.
Yes.
Now, what phenomenon are we trying to derive here? So elements that has the same electronic configuration or species that has the same electronic configuration, we'll say that those species are called isoelectric, or they are isoelectronic.
configuration.
They have the same electronic configuration. So they are called electronic species. Is that okay?
Yes, sir.
So when there's those elements or the charges, normally it happens with ions. When ions has the same electronic configuration, we call them the isoelectronic configuration or electronic ions, isoelectric ions. Okay. And again, when we are using this noble element to be writing the electronic configuration, we term that the pseudo. It's not the correct electronic configuration, but we call it the pseudo noble element or noble gas configuration. So that's just the name to that. Well, let's try to see if we can make a summary out of it, or any question, please.
Definitely, we need to print the
Okay.
predictive.
Well, so the summary is this, that we, sorry, are you asking question or you are just talking? And that thing is quite irritating. So we were introduced to this electronic configuration, I mean the quantum numbers, trying to identify these quantum numbers and their representation, how we represent them, the various orbitals that they represent, 0, 1, 2, 3. That's the representation. We say that is SP, D, and then the F. And the various shapes that they can be forming. The s orbital is spherical, the p orbital is dumbbell, the d orbital is cloven leaves, the f orbital we don't know, is unknown. However, if we, so somebody may ask, so what's the difference between the 1s and then the 2s? Well, in terms of shape, they are all kind of spherical. But then because this S is in a higher energy level than this S, the size of this S is bigger than the size of this S. Is that okay? So it has to just do with the sizes. We can't get to where we start predicting atomic or ionic sizes, but just that. So the size will just be bigger than the lower one. That's just the difference between that. I will mention that there are some quantum numbers which are forbidden. So I mentioned that. Now, the conclusion of that is that you should get yourself a periodic table, just randomly pick any element, and then try to see if you can write the electronic. Oh, please. If you can write the electronic configuration for all the elements, if possible, all the elements on the periodic table, including the F block elements. And that's where you can see whether you can follow the Avban principle. If you can truly follow the Avban principle to write the electronic configuration. When you do that, you can also see that there are some elements that deviate from the usual writing of that, so that they deviate from the electronic configuration. Okay, so they are what we call the abnormalities of the periodic table. They deviate. Okay, well, that is where we draw the curtains for the semester. The rest of it, talking of the periodic properties and the Lewis theories, we can't get there. So we'll be ending just with the modern atom, which is where we talk of the quantum numbers and then the or electronic orbitals, then the electronic configuration. It should be enough for you to pass your first semester exams. Yes, I've seen a hand. You want to mute and then talk.
Are we going to send a periodic table to the exam? So
No, please. That's why you should be fun. Just take your own periodic table, try to see if you can get familiar with the elements that are there. When you get to the exams, whatever you need, you'll be provided. You don't bring any foreign material to exam center. It's only your calculator. Even the calculator, you don't bring the back where you have those formulas listed. You don't bring it to exam center. They'll take it away and throw it away. So just bring the empty calculator. Don't write anything behind the calculator. They check that one and you can be rusticated for that. That is examination more practice. If you don't see them, just be checking the electronic board. You see students that have been rusticated. You see them, they'll display your picture, your index number, and your course. You see in the evenings, just go and stand there. You see some of the students listed. And that's why UCC stands with their exam. They don't joke with the exam. So don't attempt bringing any foreign material to the exams. When you need it, you'll be provided with that. So, but get yourself as form of learning, get a periodic table, and then try to write the electronic configuration for all. Understand when you are writing it, what it means in terms of the quantum numbers, and that is that. Now, I'll do my final revision for the semester on Tuesday. So if you have any kind of question that is bothering you, you can say that. Now, on Friday, a week today, we'll write the second quiz. So I want to just brush over that and then we'll just end it there. So if I can do enough, then Tuesday we are not meeting. The second quiz starts from the naming of compounds, naming of ionic compounds through. So if outline the course outline, can pick that. So we are looking at ionic inorganic compounds through to the nature of solutions, and then we'll also look at this chemical reactions and stoichiometry as part of the second quiz. 20 questions. So and this time we are using the SW lecture theaters, the Sandwich lecture theater. We are not going to use the new lecture theater. We use the Sandwich lecture theater, SW. I don't want to be calling it Shatawali. Shatawali have not built any this thing for us. It's Sandwich lecture theater. So that's where we'll be having it. And the time is 6 to 7. It's 6 to 7. So please note that. And don't come late. If you come late, some of you saw what happened. Even if it is 5 minutes, you'll be allowed to just write just 5 minutes, and then it's going to affect you. So the time is 6. So please note that, because we are not supposed to use the place after 7. So if you come close to 7, you are doing your own, you are digging your own grave. So please come early. And for those who are saying that the sun is going to be falling, or the sun will be dimming on Friday, we are not sure whether it will be Friday. It can be Thursday, it can be Saturday. So let's keep our finger crossed. And when it falls, I think your prayer starts at 8. So by that time you have finished your first quiz, you can go. But then those of you are thinking that you want to go home, please, you are full-time students. And so I'm talking to the Muslims. Don't try going home. Stay in the university. When we vacate, you go home. Okay. That is that. So from those topics, if you have any question, essentially for the quiz 2, you want to bring it, then we attempt that. However, I don't think we should meet again. I think it was nice doing business with you. If you have challenges, please, you know where to find me. I am, so from the course outline, you see my office, C110. So chemistry department, first floor, room 10. if you have challenges. The TAs are also available if you want to contact them for any kind of challenges. And then you can also contact your colleagues for group studies or for study mates kind of level.
Some of us couldn't join in.
So you can also contact your mates for them to help you. I will just advise that this is a 3-credit course. You really want to pay attention. So the second quiz, try to do well. If you didn't do well in the first quiz, the second quiz, try to do well. And then in the exams, you also will do well. Well, so that is all. If you have a question, we can bring it. If not, if it's necessary for us to meet again, I will send a message on Tuesday. We'll meet. If not, then it was nice doing business with you, and thank you for your time and your patience. For your patience. Sorry.
Thank
Bye
you.
bye.
God bless
Okay.
you. Sir.
Our
Thank you.
lecturer.
God bless you.
Okay. So thank you, and then see you.
Thank you, sir.
It's okay, bye bye.
Na then you be catch the say. I mean,
Sorry, love.
Say question.
Yes.